So this was a structure pop quiz 18. You can mention the doubts if you have anyone is having a doubt in question one, part A1, 2, or 3. Any doubt in question one, part A1, 2, 3? Okay. So in question 1A, students take reading to measure a mean diameter, means finding an average diameter of a wire using a micrometer screw gauge. Make suggestion for one in each case that the student may adapt in order to reduce the systematic error. In order to adopt to reduce the systematic error. So systematic error, the error which is there in the system, like the best example of a systematic error when we are using a micrometer screw gauge, that we may have a zero error in the micrometer. So like zero of the main scale, when the zero of the main scale is not coinciding with the zero of the circular scale, then a micrometer is having a zero error. This is micrometer without a zero error. But if there is a zero error, then the main scale and the circular scale will not coincide with each other. So how to reduce a systematic error? First thing what we have to do, we have to always check for zero error and then add or subtract the value according to, because a zero error can be a positive or a negative. So simply what you can do, like close the jaws of the micrometer. First, what we do, we'll close the jaws of a micrometer. We'll not place anything in the jaws of a micrometer. You calibrate the device, that's fine. You can, if you mention check for zero error and calibrate the device for that zero error, that's also fine. Or close the jaws of a micrometer, nothing should be placed between the jaws of a micrometer, and we will add or subtract that value. We call that as a zero error. Like here, when we talk about the micrometer screw gauge, so this is a micrometer screw gauge. So when we check for, if we want to check for a zero error, like this is a, we have the two scale, one is a circular, another one is a main. May not be clear because my background is blur, but I will change that. So whenever we don't place anything between the jaws of a micrometer, like here, this is a micrometer. If the jaws are completely closed, if the jaws or micrometer are completely closed, the main scale and the circular scale should coincide with each other. If they are not coinciding, it means it will have a zero error. So what we can simply do if we want to avoid this zero error, so we should first check for a zero error and then we can calibrate for the zero error, like add or subtract the value. The second part is allowing for a wire of varying diameter along the length. Like if a diameter of a wire is changing along the length, then what we should do, then we should measure a diameter from different places, like change the position of a micrometer and record the diameter at different places. That's how we can and take an average of that. Now, how to read a micrometer, I will explain that. It's not like you just directly add the values of a micrometer, main scale and the circular scale. There's a formula for that. If you want to read a micrometer, it is a main scale plus the circular scale times the 0.01. So main scale reading plus circular scale times the 0.01, that will give us a reading on the micrometer. The last part, allow a non-circular section of a wire. Like example, if the wire is not having a circular section, then what we should do, we should measure the diameter with different orientation. Like place a micrometer at different orientations so you can get an average radius or average diameter of it. So allow the wire of varying diameter along the length. So in that case, we will measure a diameter or change the position. But if we want to allow a non-circular section of a wire, we want to measure. So what we should do? We should change the orientation or different orientations. We will measure its diameter. Is it clear? About the experiments, as I mentioned, just after completing this revision of the units or the papers, then we will the topic, then we'll start the experiment part as well. Like I will discuss how different apparatus can be used. Part B, any doubt? Any doubt in part B? No doubt? Okay. Question 2, part A, any doubt? Principle of conservation of linear momentum. Actually, there's another momentum which is called angular momentum. Angular momentum means when object move in a circular path, it has angular momentum, but you will learn in A2, not in AS. Part B, 1 or 2, any doubt? Part B, 1 and 2. Okay. Question 3, part A, any doubt? So in question 3, they are saying that the diagram shows a lift system. Maybe you have seen this very common in the malls or even in apartment, that a lift system is always having a counterweight is there. When the lift is going up, the counterweight is going down. So what is the advantage of using this counterweight? Let's say there was a system without the counterweight. A motor was there, which is there at the top, and we have a lift. Example, 100 joules of energy is needed to lift, like to move this upward. So how much energy the motor has to use? The motor has to provide, it practically, it will be more than 100 joules, because what will happen? Some of the energy will be lost. But let's say the motor at least need 100 joules to lift this up. But what is the advantage of a motor or electric motor or a lift system with a counterweight? That if we need 100 joules to move this upward, the counter some of the energy is provided by the counterweight, because when the counterweight will move down, the gravitational potential energy of the counterweight will decrease, and that energy is like taken by the lift. So if the counterweight is going down and it is losing, let's say, 20 joules of gravitational potential energy, so what will be the advantage here? To lift it up, how much motor has to apply energy or produce energy? Only 80 joules of energy. So the advantage of using a counterweight, it will reduce the work done by the electric motor. Without a counterweight, it need greater amount of energy to move this lift or elevator vertically upward. So if I want to lift an object, so in short, simply we have, let's say we have a lift, a motor is there, and we have a counterweight. So when this counterweight will go down, the gravitational potential energy of the counterweight will decrease. What will happen to this gravitational potential energy? That will be transferred to the lift, so the lift will move upward. Plus, additional work is done by the motor. So when the motor will also do a work done. So in case, so what will happen? The total energy of a lift will be sum of the gravitational potential energy of the weight plus the work done by the motor, that will be equals to gravitational potential energy of the lift. So the counterweight energy decreases, motor is also providing energy, so all this energy is transferred to the lift. As a result, the lift will move vertically upward. So what is the advantage of using these counterweight? It will reduce the work done by the motor. Otherwise, the motor without a counterweight has to do a greater amount of work done. Is it clear? So the advantage of using a counterweight, it will reduce the work done by the motor. Yeah. So why the work done by the motor will decrease? Let's say to move this, we need 100 joules of energy. When the counterweight is going down, the energy decreases. Counterweight is providing, say, 20 joules of energy to the system. As it is going down, the counterweight energy is decreasing, and that energy is going to the lift to move it up. And remaining 80 joules of energy is provided by the motor. So without the counterweight, what will happen? If we need 100 joules of energy to lift it up, the motor has to supply 100 joules, all 100 joules of energy. But with a counterweight, the counterweight energy decreases. So as a result, what will happen? The motor is not have like it will not provide the same 100 joule. It will provide less than 100 joule so that the lift can move or elevator can move vertically upward. So less work done by the motor because the gravitational potential energy decrease of the counterweight provide energy to the lift. Or you can also say the total gain in gravitational potential energy of the lift will be equals to work done by the motor plus the decrease in gravitational potential energy of the counterweight. The next is part B. The electric motor raises the lift through a vertical height of 40 meters. At this time, in a time of 30 seconds, show that the output power of electric motor is about 12 kilowatt. The total mass of the lift and the people is 2,250 kilogram, and the mass of the counterweight is 1,300 kg. So if the lift move upward at a distance of 40 meters, the counterweight will also move downward at a distance of 40 meters. Because if one is going up, the other will go down. And what is the equation here? The equation which relate the gravitational potential energy. So the potential energy of the lift, I'm writing small l here, is equals to work done by the motor. We need the power of the motor plus the potential energy of the weight, the counterweight. The counterweight will move 40 meters down and the lift will move 40 meters up. The potential energy of the lift. So first we'll find the work done by the motor, and after finding the work done by the motor, power is work over time. So we'll have the work and we have the time. After finding a work, so work over time will get the power. So gravitational potential energy of the lift, the mass of the MGH, so 2,250 kilogram was a mass times the gravity, which is 9.8, multiplied by height, which is 40. The work done by the motor, we don't know. And the potential energy of the counterweight, the mass of the counterweight was 1,300 times the gravity 9.8 times the distance 40. Because if a lift is going, they're connected with the same cord. So if a lift is going 40 meter up, definitely the weight will move 40 meters down. But they will not have the same gravitational potential energies because they don't have the same masses. So 2,250 times 9.8 times 40, that is 8.8 into 10 to the power 5. 1,300 into 9.8 into 40, that is 5 into 10 to the power 5. This will move other side. So this will be about 3.8 into 10 to the power 5. That is how much work is done by the motor. But the question is not how much work is done by the motor. The question is how much power, what is the power generated by the motor? or how much work is done in every second. So it is 3.8 exponent 5 divided by the time in the question dimension. It took 30 seconds. So 3.8 exponent 5 divided by 30. What's the answer in what? 3.8 exponent 5 divided by 30, which is 1.2 exponent 4. Okay. So 1.2 exponent 4 is the power of this electrical motor. Is it clear, this one? This is a useful power, that the power which is generated by the motor. The next part, electric motor dissipates energy to the surrounding at a rate of 3600 watt. Determine the efficiency. So what is the total energy? We need the efficiency of electrical motor. If we need the efficiency can be in terms of energy or it can be in terms of power. Efficiency is a useful, because the power we already calculated, so we can use a power. So useful power output divided by total power input times 100. The useful power output we just calculated, that was 1.2 into 10 to the power 4 watts to lift this. But in the question they mention it is losing energy to the surrounding at a rate of 3600 watts. So what is the total? This is a useful one to lift. What will the total input? The total input will be the loss one plus the useful one. Because like 3600 is what is loss, and 1.2 exponent 4 is a useful one. So what will be the total input energy? The total input energy will be the sum of these two. So efficiency will be 1.2 into 10 to the power 4 divided by the total input. The total input is a useful one plus the lost, which is 3600. That will give us the total input and multiplied by 100. What is the efficiency of this system? About 77%. Okay. So this is about 77% efficient. Is it clear, this one?